Hey guys, we're going to take notes here on page 7. So let's do it. In period 8, I think we got a little bit of a head start. Not at all, I think, on period 1. So let's get to it. It says to study the long-term effects of preschool for poor kids, the researchers designed an experiment. They recruited 123 children. So that's the combined number of people in this study. Okay. Now it says researchers randomly assigned. Well, that's because it's an experiment. So there's no random sample. Everyone had to agree to the experiment. So they were assigned randomly. 62 were assigned to the first group that actually attended preschool, and 61 were specifically did not go to preschool. All right, now one response variable was there a need for social services as adults? So over a 10-year period, the 38 children in the preschool group needed social services. And in the group that didn't go to preschool, 49 needed social services. So it looks already that the group that didn't go to preschool needed more social services. So do we have convincing evidence that preschool reduces later needing social services? So we notice here that I want to put reduces maybe the other direction, but notice if preschool reduces it and the first group went to preschool, then we'd assume that they would need less social services than the second group. Okay, so this is the H sub O and the H sub A that we established. So how does the calculator come up with an answer to decide if this is a big enough difference, or is this just purely by chance? Okay, well, one new component that I want to talk about in the notes section is, well, what's happening in the calculator? So technically, to be more accurate, we should be checking, we can combine the proportion, because that would actually do what we do in the simulation in class. I'll show you what that looks like. That would mean, let's say both groups are exactly the same. How many total went in need of social services? So the combined proportion that needed social services was the 38. So it's kind of the first X value and the second X value divided by the combined, the number of combined students altogether. So out of the two groups, a total of 87 needed social services out of 123. Okay, so let's calculate that proportion is 0.71. So 71% of the whole population we're looking at needed social services, okay? Now, when we compare it to the other two groups, they were different, but maybe they're just different from this purely by chance. So how can my calculator calculus? It can calculate it by, in the do column, it creates a normal graph and it makes the mean, the difference of the two, assuming there is no difference, and then it makes a standard deviation of the difference of the two, right? The difference between the two groups. And so what number goes here? Our population difference that we're trying to approximate. And what number goes here in the calculator? It's this big honking standard deviation. And there's a little bit of a change here. So I want you to take a look. We could check for large counts using this combined proportion, right? And our standard deviation, and this would completely assume that there is no difference between the two groups. So if there absolutely is no difference between the two groups, then in the first group, we would assume 71% needed child services, and also in the second group, 71% needed the new services. So this would actually be a more accurate way of calculating by purely ignoring and assuming H sub O is true, that there is no difference between the group. If there really is no difference, then 71% of the combined group needed the services, and so that's the proportion we should use in order to calculate the standard deviation, because we could get a sample with more variability in it. Okay, so let's use this new formula to state, plan, do, conclude. Okay, so state. So we did our H sub O and H sub A, right? And then we have to just find what this is. The true difference of proportion of preschool minus no preschool groups need for social services. Okay, so that is what P1 minus P2 represents. Okay? And we have a sneaky suspicion the second group needs more social services because they didn't go to preschool, but we don't know that. So let's do our plan. We will perform A, and so let's look at this. So we have two proportions, right? And 38 needed social services out of 62, and 49 needed social services out of 61. And our hypothesis is that that second group needs it less. Enter. Ooh, critically low. Mayday. Okay. Ooh. So now I've given some meaning to what is that regular old p hat? I've kind of shown you what that regular p hat is. There's P1, P2. So P1 is 0.61. P2 is 0.80. P combined is 0.71. Okay, we already know N1 and N2. So what else I need to write down before my calculator goes dead? The P value. Okay, and the Z. Okay, so what did we perform? We performed a two proportion Z test for P1 minus P2. Or I could also say a two sample Z test for P1 minus P2. Okay. So, random assignment was used. Population is at least as large as 10 times the first sample size, and the population of group 2 is at least as large as 10 times the sample size. And the last one's large counts. And as we said, we actually have a combined proportion. So it actually would be more accurate if we combined it using this PCs. Okay, so what is it? PC hat times N1, 1 minus PC hat times N1. So what is that? 0.71 times the 62 people, 0.29 times the 62 people. So how many we're expecting? Well, based on our data, we're expecting 71% of any given person to need the social services. So if we talk to 62 people, 0.71 times 0.62, 0.71 times 62 is 44. That's good. 0.29 times the 62 is, I'll round up to 18. And now checking the other count, PC in 2, 1 minus PC in 2, we get 0.71 times 61 people, 0.29 times 61 people. That's 17.6. Pretty much close to the other 43 people. And all these are greater than or equal to 10. So large counts apply. So we can use this, and we can use Z. And what would Z calculate? it would take our P1 minus P2 and it would subtract it from our null hypothesis, our regular P1 minus P2, and it would put it all over the combined standard deviation. So that would look like this. Okay. So let's plug all that in. P hat 1 minus 2 was, what did we get? 0.61 minus 0.80. So negative 19. Minus P1 minus P2, which our null hypothesis is that number is 0. So minus 0 all over this gobbledygook. So that's the 0.71 times 0.29 all over 62. And the 0.71 times 0.29 all over the 61. And the calculator did the work for us. It came up with the z-score of, we already wrote it down, negative 2.32. Negative 2.32. So what does that tell us? Whoa. This is 0, right? Then we have a value that is 2.32 standard deviations from the mean to the left, which is why it's negative. And that means that the calculators come up with the area under the curve. The area under the curve here is 0.01. So we're ready for our, we did the do, we are ready for conclude. Since alpha equals 0.01 is less than 0.5, we reject the null hypothesis. We do have convincing evidence that preschool, now I'm just going to copy the sentence. We do have convincing evidence that preschool reduces the later need for social services for children, like the ones in the study. Reduces the later need for social services for children, like the ones in the study. Okay, now what? Based on your conclusion to question 1, could you have made a type 1 or a type 2 error? So I walked through door number 1, right? I rejected the null hypothesis. So I maybe could have, I could have committed a type 1 error. Is a 5% probability purely by chance, since alpha is 0.05. Awesome job. Thanks for joining us, guys. See you next time.